Very good, welcome back. So, just to finish up, how did I implement this particular request of mapping a satellite image to a distributed surface? I used the Python programmable source in this case, and I declared a grid resolution of 90 by 180 degrees by 1 for the radius. So I'm going to build a 2D surface in 3D space. And here I said the global dimensions, what extent is the global dimensions of the mesh, should be exactly this 90 by 180 by 1. And I say, by the way, I'm going to run in parallel, so I can, meaning I will implement it, but ParaView, you can ask me for local partitions. That's what it means. Now, the computation itself, how does it work? I get my executive, and from the executive info, output info, I get the global extent again, which I will use to understand where am I in the overall picture. And I get the so-called update extent, which is specific to my pipeline. Each processor has a local vision, if you want, of the global pipeline. In other words, the dimensions here that I get are embedded into the global dimensions, which are here, global dimensions. For my particular processor, you have to reason like this. I am processor 0, I'm processor 1, etc. My output will be using the local dimensions. Next. I have to define an x, a y, or rather a radius, theta, and pi coordinate axis. There are numpy arrays of dimensions using the global dimensions. Here, from 1 to 2, that's for the radius, there will be a single value. For theta, from 0 to minus 2 pi, and for phi, from from 0 to pi. Now, you can use minus pi over 2, minus 90 degrees, plus 90 degrees, or 0, 180. It will really depend on the convention. I use that particular convention, but then it's all a matter of trigonometry. Those are the global space. But then using NumPy array slicing, I slice them exactly for my local coordinates. All right? Those become the local resolution in X, Y, and Z. And I need to compute the so-called texture maps, which are from 0 to 1 in the horizontal space and from 0 to 1 in the vertical space, to take the satellite image 0 to 1, I map it over the full image. Now, it's a little bit of a complicated example, but just get the main logic. The main logic is you allocate global axis arrays, then we slice them using NumPy, using traditional Python conventions, and we generate this vector using the different coordinate axes. And then the trigonometry is here. That's the standard formula from Wikipedia or any other book. I set the points, which are the coordinates of my mesh, to be x, y, and z as a vector. I add, just for debug purposes, the radius, the theta, the phi arrays, and then I add my texture coordinates. And I will demonstrate how it works in my window. There we go. Projects, ParaView, Python, ParaView, script equals PV, spherical. Okay, here's my map. Here's my globe surface. Here's phi, the angle phi. Here's the angle theta around the globe. Okay, 0 to 360 degrees, if you wish. And then ParaView has this nice property in my display object to be able to assign here a particular texture. So I load a particular image and I give it this image of the Earth. And there's my Earth here at the right place, okay? There's Africa and so forth. Let's look at the texture coordinates. There's the texture coordinates from 0 to 1. What this really means is that all around the grid points, I've set those coordinates to increase from 0 to 1, and then I will use that with the satellite image to say, hey, you need to map these using this particular scaling. Let's look at the Y component of the texture. And sure enough, it's from 0 here to 1 at the top, which means I can take my flat image and then warp it. This actually I use on a single processor because that's how I had set it. Now let's go to settings. I go back to my parallel 8 processor thing. I quit and I relaunch. And there's my grid again, surface. And now I have the processor ID. So there is my decomposition of the globe on 8 processors. And if I go to my properties, I do the same job again. Load images. And there's my globe now partitioning on among 8 processors. And what matters is the texture coordinates. And we see that nothing has changed. If I look at the X component, each partition using the slicing of the Python arrays through the coordinate arrays, I got this all done perfectly. So in case of a 3-dimensional spherical grid, I would apply this on a fixed radius inside the spherical volume, okay? Because we have a 2D satellite image, we can only map it on a 2D surface. Using the extract volume of interest filter, I can extract any radius through my spherical grid and then apply this technique. Good. Volume visualization. Here are the objectives of the day. Show a fancy movie, and then give you really some practical tips on, because there's a lot going on in volume rendering. It can be very heavy in computation. It can be very disappointing. That's probably most of your experience, no? The beginning, it's difficult to make anything nice. I want to discuss mesh types, data types, VTK pipelines, ParaView, then present the NVIDIA Index plugin, also present the Intel Osprey plugin, and then I have some demos and exercise, and if we have time, we need to practice those. All right? So pseudo volume rendering to begin with. I'll refer you to the textbook, page 218. I meant here to add a picture, but I forgot it, so there's nothing to see inside. Sorry about that. Mesh types. We're back to the mesh types here. Not all grid types can be volume rendered. That's the first thing to know. Image data, yes, absolutely. Why so? Because the volume rendering technique comes from medical imaging, CT scans, magnetic resonance imaging. All those are perfect stack of images, perfectly Cartesian, regular in space. So, of course, VTK image data, yes. VTK rectilinear grids, which would be this, that doesn't work. You cannot volume render. It's not implemented currently. Structured grid, no. Unstructured grid, yes. I say yes with some hesitation. The standard ParaView volume renderer is very poor, very slow. Don't use it. The great strength of the NVIDIA plugin is that it can do real-time unstructured grid volume rendering, and I'll demonstrate that. So there is really an immense benefit at using the NVIDIA plugin. Yes?
Can you also use it for particle data?
Yes, I have in the past, going through a resampling step first, unfortunately. You can also do what is called splatting. For each particle, you can it's like saying particles in space are like snowflakes in the volume, and then the snowflakes fall on the ground and they accumulate. Well, the ground is your image, your screen space. So this splatting, this so-called splatting technique is saying, compute the projection of something looking like a snowflake, so a little hazy spherical shape that gets projected on the screen, and just like snow falling on the ground, if it snows more on this area than here, you'll have more opacity on this side of the screen. It can be done. It's not so easily accomplished. Array types. Not all array types are supported. Some of them will be transformed under the cover. This is also very important to understand. For example, I forgot now, the NVIDIA plugin supports one and not the other. It doesn't support short, I guess. Is that right? And it supports unsigned short. It's one of the two. It's not so important. You have to know which one. And if it's not implemented, you can convert it to the supported type. Float, single length versus double, you have to understand what is going on. By default, the kitware implementations of volume rendering will actually convert your floating point data to 16-bit integers. So that's also to know, to be aware of that. If the data type is not supported, for example, you can convert it. So back to Python, we have this nice little filter called VTK image shift and scale. This is typically used for VTK Cartesian grids, so VTK image data. Here's how you would do it. Inside your Python programmable filter, import VTK. Here I need information about the so-called integer types. So from NumPy, I need to import ii-info. That's all really the required information. Now, perhaps I will demonstrate this interactively, but as you connect a programmable Python filter into your pipeline, by default, you have a name called inputs. And there's several, it's an array because you can have several inputs going into a programmable filter. Here I have a single grid. Downstream in the pipeline, I have a programmable filter, so my input is inputs of 0. Point data, as you recall, is the dictionary where I have all my skill field stored, and I index that with the name of the scale field I want. In that particular example, I had some DICOM data where the image was called meta image. And then you get a get range, which gives you the minimum and maximum of your floating point or your integer, your short. In that case, it's 16-bit integers, so they are shorts, and gives you the range, minimum and maximum. I get a filter, image shift scale. I set the input to the filter to be the object, the grid object. I shift it by -1 times the minimum, and I scale it by the maximum possible value a 16-bit unsigned short can store. In that case, I spread all my scalar ranges to the minimum and maximum possible values of the range. And I say, I want my output to be of type unsigned short. And here you have multiple choices. You can convert to basically any data types which VTK supports. You update. This is a way to force the execution of the pipeline. And you need to do this execution. You need to trigger this execution, and once it's done, you copy. This is VTK syntax. You do a shallow copy, which means you only pass the pointers in memory. You don't duplicate data. You pass the output of the shift and scale to output. Output is also a predefined name, so the input to the programmable filter by default is called inputs. The output by default is called output, so it's a predefined name you don't need to worry about. For example, you could also do something very quickly without scaling and shifting using the Python calculator. Same syntax, inputs of 0, the point data. RT data is the typical scalar name from the wavelet source. So if you, on your laptop, get a wavelet, do this. This is a one-line thing in your Python calculator. And you output this as type, floating point 32. More explanations in the guide, paragraph 592. By the way, this is the first time I talk about the Python calculator. What's the difference between the Python calculator and the Python programmable filter? The difference is this, one line. So if the thing you have to do is one line, it fits in there perfectly. It can be a long line, but there cannot be if, then, else, etc., etc. Okay? So this is actually very convenient to do simple, take one scalar field minus another scalar field, take the magnitude of a vector field, take the gradient, take anything that fits in one line. And paragraph 592 has the list of all the functions you can do with a single input. Yeah, so I guess here I have to show the little demo, and I will. Pseudo volume rendering. How was it done in the early days? How was it conceived? Take a volume of data, calculate. So that volume of data can also be, it doesn't have to face the viewing point. It can be in space, orientated arbitrarily in space. Calculate the orientation of that volume, and then take slices through this volume perpendicular to the viewing direction. Make those slices transparent, and then you accumulate them. And you have a pseudo look inside the volume. I think it's best. So, yeah, you compose translucent cut planes. You can do this with any grid types. That's the advantage. The more planes you use, the better quality you would get. But of course, as soon as you move the volume around, those slices you've done through the volume, they're not going to face you anymore. And I'm going to demonstrate that to you right there. That would be, there we go. All right. ParaView minus script equals PV pseudo volume. It's probably going to run on 8 processes. I don't want that. I'm going to switch back to a single one just to make it simpler for the moment. Apply, OK. Exit. There, a single task, a grid. So this is using the Plot 3D reader, which outputs a curvilinear grid, structured grid. And what have I done? Forget about the contour for the moment. Well, actually, the graphical user interface tells us what I have done. I've taken a cut plane here, and at regular interval, you can see here the offsets, and you can distinguish those translucent planes. I've taken slices through the volume. All right? Now, when I'm facing here, when I'm perpendicular to those planes, it looks pretty good. Yeah. Okay. Now, look, now, as soon as I'm off, this is useless. Okay. But anyway, this is pseudo volume rendering. So if you had an automatic way of always moving those cut planes to be perpendicular to your viewpoint, you'd have the cheap volume rendering thing available. Well, basically, that is what is now done on the GPU at high speed by the more modern volume renderer. No. There we go. I just need. All right. A side note, depth peeling. What is depth peeling? Compositing translucent object is not something trivial. If they are always exactly one behind each other, cool. It can work. But it can also go wrong. I'm going to demonstrate that. I have a script called the depth peeling, and I have a movie. Let's watch the movie first. typical situation, I have this is molecular data. I have a molecule. I compute some isosurfaces of electron density and make those surfaces translucent, and look at what happens. I got all kinds of weird effects. Now I switch to depth peeling. That's the correct rendering you want to see. Okay? And by the way, I've done it on purpose. If you watch the frame rate, I'll play the movie again. The good solution is 10 times slower, but it's good. It's the correct solution, so there is advantage. What is happening here is that we have multiple objects at different depth, but the compositing only knows about the transparency and the color of each pixel. So it gets confused by the depth, and it messes it up. Depth peeling, here we are 10 times slower now in terms of interactivity, but depth peeling does this just like peeling the layers of an onion. That's where the name comes from. There. So the movie proved the point. And in ParaView, you have in your settings of the render view, I think by default it's on. By default, there are 4 layers of depth peeling allocated. Let's go to my depth peeling example. I forgot where it's at. I'm not as organized as I should be. I apologize for that. Of course, it's called depth peeling. What else? That was pretty easy, no? ParaView. PV depth peeling, PV. I will give you all of those scripts so that you can exercise them at home. There. Same data. There's my molecular data here in the middle. As I move around in space, everything is cool. Yes, because depth peeling is on. Let's go to settings. In the render view settings, we have here translucent rendering option on, and I have 10 peels. If I turn this off and I say apply, there is, I'm back to those really weird effects, okay? So be aware that depth peeling, I believe by default is on. Be aware that it will consume more resources on your graphic side, but there's a price to pay, but the quality, the rendering will be the correct rendering. I'll switch back to depth peeling on so that I don't forget for the next time. Depth peeling on, okay. All right. We're there. Volume rendering a structured grid. Yeah. Volume rendering. I'll read this again. Okay, my structured grid. I'll get rid of the slices. Delete this. The contour I can keep. If I switch the display here to volume, it says cannot execute. It's not implemented, I told you. So, solution, I can tetrahedralize it. It's going to cost some memory, but let's not worry about this. I call the tetrahedralizer filter. I apply there. I have something that looks like the same grid, but it's now an unstructured grid. I can say volume rendering of this. Okay? And now I want you to watch at the bottom of the screen here. Right here. Okay, you can't read, but it says OpenGL projected tetrahedral mapper. By default, there's this mapper called, it's 30 years old, this mapper. I've looked at the publication, it was 1990. It works, but it's pretty slow. What does it do? For every tetrahedral cell, a tetrahedral is made of 4 faces. You extract those 4 triangles, you classify them, you depth sort them, you cut through them, and then you do the back to front rendering of it. It's pretty slow, and it gives some okay results. And I want you to look at, I want you to see the options that are available. And I have the so-called projected tetrahedra, Z-sweep, Bunny raycast. All those options don't use them. They're historic thing. They're low performance. They're no good. The final option is interesting. We'll talk about it. It's resample to image. This is a filter that will resample your grid. Actually, I will do it because it has some interesting things to know about. If you resample an object of arbitrary shape in space, resampling to a grid can only be done with a rectangular box. That object is inside. Anything that's outside the object but inside the box is going to be data you need to throw away. This is done here, if you see, in a rather approximate fashion. So we're not doing so well. Finally, there is the NVIDIA Index plugin that we're going to use, and you'll see the difference. So I will just switch to it directly, and there is a nice, clean, high-performance renderer of the volumetric data with the unstructured data. Now, if I edit, you'll see if as soon as I edit my transparency function, I can see inside the volume, okay? In purpose, I've put this isosurface in the middle, which is a fully opaque object to demonstrate that I can do proper compositing of polygonal surface and volumetric data. And I have here this really fun to play with volume rendering. Finally, I have an interactive renderer that is good to use. So I'm mixing here opaque and semi-transparent stuff. This is great. It works. The last option, resample to image, is interesting because it's multi-threaded. It's going to use all cores on your machine. So even if you're running here client only on your desktop, it's going to go full speed, and it's pretty good. So do use it. It produces a VTK image data grid, and of course, VTK image data is very well supported in volume rendering. And it's exactly what I have used for this movie here, which was done in collaboration with a number of folks from University of Twente in the Netherlands, and Alexander, who's right here, is the main author of the scientific work and the inspiration for this movie. It has cost me quite several weeks of work. Don't think it came for free, but this was really a great accomplishment. The grid here is of type VTK rectilinear grid. Yes, right, yes. So I resample it. And by the way, Alexander's grid is of resolution 257, one of the main grid we worked with, 257 by 1024 by 1280. Gosh, that number just doesn't fit right on the GPU. 257 is not a multiple of 16. It's exactly 256 plus 1. So I resampled it to 256 by 1024 by 1280. That fits in nice blocks of the GPU, really high speed. Otherwise, you got one extra pixel, one extra lines that you can do it, but it's much different in terms of performance. Here, we don't see that one grid line is missing, right? It's been resampled. I'll play the movie again. So, because I want to explain a few things about this. So this is time-dependent data. Of course, loading the data is expensive because it's HJ5 data, it's a large grid, and it's difficult to not benchmark, but to fine-tune a volume rendering of the sort when you have large data. Fortunately here, it's quite homogeneous in space, so I actually reduced that to something small that could fit on my laptop. I could play a lot with a small subgrid of the volume and then experiment with the column map. And that's really the key to the volume rendering, is to use the proper color transfer and opacity transfer function. And you have to use a very light hand. Don't go 0 to 1 and look at those numbers. 0.08, that's a single peak, I have to point it to the, with the point here. Everything is completely transparent except here, just a very small triangle shape function where it's somewhat semi-transparent, and that gives us that particular rendering. Then, of course, we had to play with the colors quite a bit to get the proper thing. But so first advice is start very low with your transparency, and then bring up the volume as you go. All right.
How long did it take to edit and render and enter to get this?
Oh, I don't want to tell you because my boss would get angry. Took a long time. Original is rectilinear. It actually, ParaView used to support rectilinear, but it would do rectilinear of hexahedral cell, very slow. So we had to throw that away. I just said that. We resampled the original grid to that nice, good number, power of 16. I said that this takes the longest time. And then we have three solutions, which I tried them all. Kitway, the native GPU renderer, yes?
Just on this note, I also have experienced these issues trying to start on the right color map. Yeah, it's can be very complicated. You will have the histogram of the
Yes? That's a very good comment. I have that in a few slides later in my presentation. Yeah. Using a histogram of your data can help you look at the density distribution in your data. If you look at gradients in your data, you can also get some great insight into how to tune the volume rendering. Now, those benchmarks I did back at the time in November. I have to be fair, I would have to rerun those benchmarks again because a lot of things have changed. So let's take them lightly. The native renderer with ParaView, the kitware renderer, shows the highest frame rate. Well, it's easily explained. It converts the floating point data to 2-byte unsigned integers. So it actually has to do less work, less data transfer, less everything. Index was pretty good at 45 frames per second. So there is, I think somebody was asking how interactive it was. 50 frames per second is excellent. Osprey is another solution by Intel, which I tested on the other partition of the Daint machine, which is fully multi-threaded. And actually, I was getting some pretty good numbers with, it's a little bit comparing apples and oranges. They don't do all the same things. They take shortcuts in terms of interactive, in terms of progressive rendering, etc. So take those kind of lightly. ParaView converts 32-bit to 16-bit integers. I've looked at the time. Here's a good, immediately, because you have less data to store, you have less memory occupied on your GPU, and this I would have to re-evaluate again. An illustration of the 30-year-old unstructured grid volume renderer implemented still today in ParaView. This is what I was telling you. For each tetrahedral, get all those triangles and then send them over to the pipe, to the OpenGL pipe with transparency thing. All right. Index is what today is absolutely my favorite solution because it's improved quite a bit since November, and it's now integrated fully into ParaView. It supports unsigned car, short, and floating points. So we know now how to convert to those types if we don't have them. Interesting, and this is a great contribution by the plugin. It does more than what the default kitware volume renderer does. It has the so-called visual elements, features, which enables us to enhance the perception of the volume. I'm going to demonstrate that in a second. So there are four choices: none, the standard; isosurfaces, which I really would call iso volumes, and I will demonstrate the why of that; depth enhancement, isolating features with high opacity. I will demonstrate that. This is very useful as well. And edge enhancement. I also have a good demonstration of this thing. Everywhere there's a silhouette in your rendering, there's a nice little rendering done to enhance the perception of that rendering. So there it is, my first demo, the PV index. ParaView. PV index, this guy. All right, here's a tooth. I'll give you the data. Actually, I've prepared the data already on the Scratch file system of Daint, so we can exercise it this afternoon, most likely. Properties. None. Ooh, I don't like that. The crash you're seeing here, it's not the NVIDIA plugin. You might have seen that all morning. My ParaView on my laptop crashes every time because I work with kind of a development version here. Anyway, those are the edges, the silhouette edges on this volume rendering. All right. There is the rendering, and we can see already an internal material boundary here, which I can also augment or visualize via the, so here's the color map I use, and if I compute a gradient and a slice of that gradient, there it is. Here's the tooth. Let me remove the volume rendering for a minute. There. So this would be a technique to use. I mentioned it a few minutes ago. Take your data set, looking at a histogram. Yes, that's a good point already. And then looking also at the gradient in your data. And here we see those material boundaries, the boundary between the tooth and the outside, and then the internal boundary here that is a somewhat strong gradient in your data. So if we can highlight and tune the color map and transparency transfer function based on this gradient, then we would automatically throw away all the data with low gradient and keep the high gradient data. So there, I'm going back to my rendering here. For information, the grid is of size, it's pretty small here, it's about 100 cube. And if I modify my transparency function, as you can see here in real time, I get here the high material, and I can, of course, go crazy. As I told you, you have to use a very, very light hand to highlight data in your volume renderer. So that's the first demo I have here. Then I have another one called PV index threshold. I forgot what it does. Let's find out. Yes, that's a good one. All right, take the wavelet. Take the wavelet, resolution 100 cube, more or less. Threshold that. So I threshold between those two values, which means this is now those are now the cells in between those two scalar fields. This is seen as a surface area, okay, nothing fancy there. If I make a volume of this, it does this awful thing. Okay, you've seen it here, very slow, and this is completely useless. That's the default renderer of ParaView. If I switch now to this other window, this is now using the NVIDIA plugin. Okay, here real time we have, that's a good point already, but it's very fuzzy, pretty useless as well. Until I use the index visual element called depth enhancement. And there now I have a very, very nice, let me turn off the boundary. I have a very nice rendering of my volume with depth enhanced perception. Okay? So that example uses the wavelet, so it's easy for you to play with. I've also copied it to Daint. For this afternoon, we can play with it. All right. Does it require a NVIDIA GPU? Yes, it does. We have a few of them in the machine room. Okay? Yeah. So, on your laptop, yeah, I guess you have to have an NVIDIA GPU, right? There's no other way. But it's worth it, right? It's really good. And now the big benchmark I did, and we have that data. Unfortunately, I don't have the release authorization for this data. So I cannot publish images of it in a public fashion. I converted this to unstructured grid. Only for the motivation was the benchmark, the unstructured grid, because it's volumetric data. I can do faster rendering without conversion with the image data. Yeah, this is just an image. So converting it came up with 770 million tetrahedra, and I rendered this on Piz Daint in real time at interactive frame rate. Yeah, I just did it, and I have the movie here, but I think the movie I play over here. Oh, this is showing the interactive. You see my mouse pointer. This is a screen copy on my desktop. So here I'm moving through the, zooming through the volume, and this is capturing the data. I can see here that I have 770 million tetrahedra rendered on the machine. And this is my color map here. As you can see, mostly transparent, and then exactly where the bones to tissue materials are, here I raise the opacity of the data. This was done in November on 64 GPU. Since then, I've repeated the same benchmark on half as many GPUs, which means the index plugin has improved quite a bit in its memory consumption and etc. So I have great results with that. All right. So if you have an NVIDIA GPU, you can exercise the plugin already on your laptop, standalone. You can use the wavelet. You've seen there's a great example. You generate some simple data, and then you exercise the volume renderer. To use it on Daint, here's what we're going to have to do this afternoon. Use a single MPI task per node. In any case, we have a small number of reserved nodes. So take one each and nothing else. You have to connect to ParaView. We'll see how we do that. And then you look on the queue system for your ID. For example, if your student username is stud8t with the -L, it will give you the need ID. This would be the output of the line you see. PV server, the ParaView server, running with your username for 20 minutes, and it's using the compute node need 07280. You need to ping for that address, like this. It gives you that number. And you need to use an NVIDIA config file, an XML file, which you copy to your config ParaView directory. And you need to set the discovery address to that IP. You do this at the time before switching on the plugin, and then you'll get the thing enabled. Column map, since we've talked a lot about the column maps, since a big amount of work is setting up the right column map, this morning I said I share Python script mostly. I can also share column map very simply. So it's very easy. You go to import and export in the column map settings. You say OK, and it exports JSON files, which you can easily email to a colleague working many miles away from you. So here I have, once they are exported and imported into your environment, then they come back. So I have here, for example, the temperature column map predefined for this nice visualization of the DNS I showed earlier. I have one for medical, and so forth. So you can customize your column maps for all your different projects. Something new in ParaView 5.5. You can do isosurface rendering directly on the GPU without creating polygonal objects representing the isosurface. Let me demonstrate that to you. There's a nice blog article. You can read about this at this address. The traditional visualization is use the contour filter, create a geometric object, yeah. And of course, every time you change the threshold, you have to transfer data from the CPU to the GPU, and it's not very fast. And the computation itself of the isosurface can be pretty slow if you have large data. New in 5.5, you render the isosurface directly on the GPU. There's no mesh. So you cannot save the isosurface as a mesh. It doesn't exist. It's only there on the GPU. I will demonstrate that right away. How do I do this? ParaView. So this you can also test very simply. Get ParaView, get a wavelet, source, wavelet, properties. So I keep changing those numbers, and I need to teach you how to save that to be the default. There's a button here which says here, save the current settings. I always forget to do it, so now this is saved for the next time. Okay, I have my volume here, traditional volume with my scalar field. There we go. Typical classic way would be to do isosurfaces. Here, if I compute 1, that's the one right here that we know about. If I delete this and get a range of 10, those are the isosurfaces. See, the computation took a bit of a, and to better view it, I clip it in half and I give it colors. I'm almost there, and there I am, with concentric If you want isosurfaces, it looks pretty good, yeah. But you can do much better. I turn that off completely. I go back to my display. I turn it on. This is the surface representation. Now I go to volume. Okay. And I go to this new setting in ParaView 5.5 at the bottom of the screen somewhere called Show Isosurfaces. There's one. In this case, it's advantageous to turn shading on. And there. So I have one isosurface. And like before, I can do a range of isosurfaces, and I have them here. And I can also clip and do all those other things. Switching to the NVIDIA plugin, I can do something very similar, but not quite. There's the NVIDIA plugin. The NVIDIA plugin has the so-called, I forgot, I don't see it. Why not? Isosurface here. There we go. And you have that volume rendering of the isosurface. Now you have two sliders, one minimum and one maximum. Unfortunately, the maximum can be lower than the minimum, which needs to be corrected. I've already notified NVIDIA about this. But you can see it's real time now. It's real time. And as I change the transparency function here, transfer function, you see that I make my volume more or less visible. And I don't know, I forgot if I turn on the shading would also improve the rendering. So this is it for the volume renderer. Let me go back to outline. Let me go back to the standard. Actually, I don't need the outline. Here, the standard polygonal display of my half of my volumes here. It's nice, but unless you move it around, the perception, it's kind of hard to distinguish here what you see. I'm now going to exercise the Intel Osprey renderer, which can do real-time shadows. And you'll see the difference and the advantage of using it in that particular settings. So at the bottom of my viewing window here, I have Osprey. If I turn shadows on, there I have, okay, it's a lot of polygonal objects, so it's kind of hard to see, but I have real time here, shadow computations of my volumetric data. So perhaps I can reduce a little bit the number of isosurfaces I have, because it's a bit too many. And that would help us appreciate the effect of having real-time. Oh, by the way, full screen. I can have full screen shadows of this geometrical object. Okay, that can help a lot in depth perception. I'm not using the GPU anymore. So the question to NVIDIA or AMD or other GPUs, here it's all CPU, all threads, and it's really quite performant. So this is very nice. I like that a lot as well. There, back to my presentation. I forgot where I am. So GPU rendering, we've done this. Yes, we've done that. The tooth. We've talked about the histogram. I've talked about looking at the gradient to improve the rendering of the volumetric rendering. Unfortunately, in ParaView, you can only have two transfer functions, one for color, one for transparency. Visit actually has a mode where you can have a two-dimensional transparency function. And in that case, you would also use the gradient, for example, to modify your transparency. I've prepared an example with the tooth, which does just this, in VTK now. So this is pure VTK Python. With this particular test, we can test 1D traditional volume rendering, 1D with a opacity transfer function, and then we can also test the two-dimensional opacity transfer function. Aha! Is all of this, we're getting close to the end, that's good. Is all of this too complicated? Kind of, eh? You can do this on the web now, using a derivative of ParaView, using JavaScript called ParaView Glance. So there's a blog article that I would like to point you to, and then, whoops, I'm sorry. And then there's this link here, this app on the web. Actually, I meant to do this, but on my Ubuntu side, which would be much faster. Oh, and then we still have to talk about this. There we go. So here's the app, ParaView, on the web. I've promised that on the program. Load a file. I just have to get to my data. Project volume rendering volume VTI. Okay. It's perhaps, yeah, I guess I forgot which file I'm supposed to load here. Perhaps the file I selected is not the right one. Or is it? Oh, the tooth. That's also a format that's not. Which one is it? Volume. There we go. We've talked about histogram. This is something that's automatically loaded here in this web application. As you load data, it will compute a histogram of it, and then here, for some reason, I don't see any data. I don't know if I need to reset something. But you have the histogram, and you have this nice way of using Gaussian type shape of to manipulate your color map. So I got kind of lost here. Just a second. Yeah, I'll have to redo the demo. I got kind of lost. All right, so let's just finish with this. It's an app on the web. You drag and drop your file into the app, and you can do some volume rendering. I have one more thing that I have already loaded on my web page here, and I want to demonstrate it. You've seen my picture of the texture map of the sphere, of the satellite image of the Earth. You recognize here the ParaView color map. And now I can go through different visualization of this climate data. And if I look here through the Pacific Ocean, I can look at the different time step. You can see those rolling vortices here, the tropical storms going through, etc. And I can also go a little bit slowly to different view of the Earth. Okay, where's my pipeline? Did you see me load any data? No. This is something new in ParaView as well, called Cinema. I'm going to demonstrate that now live on my laptop, and you also have it working on your laptop. So I'll stop this. This is ParaView on my laptop here. Download ParaView, bin ParaView. I'm going to import a Cinema database. There. There's my data. I can interact with it in 3D. It's kind of limited. It's kind of choppy because it's low resolution. Okay, what is it? Cinema is the concept of saying, I have some very large data. I'm going to make a visualization of it, and it's difficult to know what is the best orientation to look at the data. It's also, I also want to give some freedom to the scientist to explore the data. I'm going to automatically select or compute images from different orientation. So what I'm doing here, it looks like a 3D interaction with a model, but it's not. It's just me interacting with images. Okay, so it gives the feeling of 3D mesh polygonal display, but they're only images. Okay, here's the interface. If I say export scene, if you have a given scene, I'll give it a different name, CDB. There. There's the graphical user interface for Cinema. You select the image type. You select the camera type. So here, in this case, azimuth, elevation, roll. And at that given resolution, 12 iteration in the phi direction, 7 in the theta direction, 1 in the roll direction. I'm going to generate all those images. I'm going to create a database of images, which in any case, if I have large, big terabyte data, is still going to be much smaller than my original 3D data. I save this into a so-called Cinema database. I can replay it from within ParaView. I can also ship it to my colleague across the world, and using the web interface, he can animate through this model. So this is exactly what I had here. This is now a web page here. This is the viewer of Cinema. And I'm now interacting simply. See, it's pretty smooth. with the model. So this would not give you a mean of exploring your data with new things, but it gives you kind of a pseudo travel through pseudo exploration of your data. You can use a resolution as fine as you want. You're going to generate more images. But further, it's not this interpolation of different, okay, here we interpolate orientation. You can interpolate also and create multiple images of certain parameters. For example, if you had your big climate data and you would look at isosurfaces of temperature, you could animate those isosurfaces of temperature through this database and give the end user, the person who does not want to open up ParaView, does not have access to the original simulation data, that person can actually also animate through those temperature surfaces, etc. So if you go to the website, I had here. So this is the blog example. Really, it's image-based. That's what it is. And they have here examples of the animation. Okay, perhaps not that particular page. No, this one I've done already. So I want to go back to cinema. Okay. Cinema. No, that's not the one. I'll have to find the correct URL for it, where you have some canned examples of different scenarios of visualization. So cinema is also available in ParaView, and I encourage you to try it. Here's the interface. So basic interface here would be camera animation, but actually let's do the full exercise. Here I delete this. I take source wavelet and an isosurface here in the middle, okay? And if I do export cinema database, thank you. If I do export scene and I say like this, I select images to save, I select the azimuth elevation roll, I can track my contour object here, I select here a range of isosurfaces, okay. I say save. And now it's going through my whole 3D data set, computing the different orientations, the different animations of the filters. The point is that a big part of the cost in visualization is loading data to disk. Once the data is in memory, it's actually pretty fast to go through multiple parameters, especially if it's only rendering interaction, okay? So there you see it. It's animating through the threshold of my isosurface value. At the same time, for each of those values, it will animate the orientation. And I'll have a database where I can simultaneously animate the orientation and scalar value of that isosurface. I repeat, the big cost is loading the data from disk. Once it's in memory, we can actually do things pretty quickly. Good, I think we'll stop right here and take the lunch break. We'll let this finish. I'll reload it after the lunch to see how we play with it. Okay? Thanks.